We're on the last leg here of this chapter of electric force, and you've gone through quite a few things up to this point. You've learned what force is, you've learned how to quantify the force between two charges, you've learned how to quantify the force of multiple charges on one charge by adding the vectors by the component method. You've learned the effects of a dielectric in the field and how much that influences the force between two charges. We've got one more thing to cover, and that's what the field looks like, what the area around the charge is going to look like. Before we get to that, I want to wrap up just Coulomb's law. Coulomb's law is very similar to the law of gravitation. You remember in the law of gravitation, F sub g was the force of gravity was directly proportional to the product of the masses, and the force of gravity was inversely proportional to the square of the distances between them. And then we were able to get F sub g is equal to g m1 m2 all over r squared. It's the exact same relationship, and again, let me state Newton's law of gravitation. Hopefully you remember that. It's kind of a big deal. That the gravitational force between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distances between them. Coulomb's law sounds really exactly the same, except for now we're talking about charges instead of talking about masses. The electrostatic force between two charged objects, not two objects, but two charged objects, is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. I would expect you to know this statement of Coulomb's law for the test. There's really not a notes portion of the test, but this is something on the test that I would expect you to be able to tell me. All right, so you should know that that relationship is exactly the same as the relationship that exists in gravitational force. And you also know that there is a gravitational field around a planet, an area where the force of gravity starts to be felt and influences anything that comes into that field. It's the exact same notion that we have for electric charge. Just like there's an electric force, and just like there's a gravitational force and therefore gravitational field, there's an electric force and therefore an electric field. Let me explain this also before I get into it, because this is a little bit more abstract, and so I want to be as clear with this as I can be. We've said in the past that gravity and electric force are action at a distance forces. They don't have to be in contact with the object in order to push or pull the object, unlike friction, unlike tension on a rope or wire, unlike contact force. Action at a distance forces can influence an object just because the object comes within the area of influence, and that area of influence is called a field. An electric field is an alternate way of describing electric force, just like a gravitational field is an alternate way of describing gravitational force. And let me give you the drawing, and then we're going to talk about it. First of all, I have two charged objects, and they're under a box because you have no idea what's going on. All you know is that you have put a test charge here, and it moves in this direction. You put a test charge here, and it moves in this direction. The field exists, and again, pause this video anytime that you need to in order to do the drawing, in order to write down the things that you need to write down, but then you're not waiting for me and you can just jump in as soon as you're done. So I kind of like this way, but I wouldn't mind feedback from you if it's just too hard to have to keep pausing and starting and pausing and starting. Just let me know that. I want it to be as efficient for you as possible. Okay, the field exists because of the charges that are already there. It is independent of the test charge. The test charge is there to define the hills and valleys, the strengths and weaknesses in the electric field. It does not affect it. So if I have a charge, and we're actually going to do lines of force in a little bit, but if I have a charge right here, let's say that it's a positive charge, then there is around my positive charge an area of influence that positive charge is going to exert on any other charge that comes into that area. Now, here's the key point. this field exists even if it's just one charge. It's not exerting its force on anything yet, but there is a field around it that is ready to influence any force that comes into, or any electric charge that comes into contact with it. The field is there regardless of whether or not there's another charge to be influenced by it. So what we do then is we take a test charge and we put it in the field to see what happens to it. What is the effect of it? What is the influence on it? But I don't want to know what the field is because of the test charge. I want to know what the field is regardless of the test charge. So we're measuring this and trying to get rid of the test charge because I want to know just the field. A couple of things about it. First of all, test charge is not always, but by convention, typically it is said to be a positive charge. And I'm going to deal with it that way, but if you go on to take physics, don't be all stressed out if your professor says a test charge could be positive or negative. Both ways are talked about, and it's just easier if I make the convention that it's always positive. Then you'll just know automatically what's happening because you can predict this is happening because I have put a positive charge here. So let's assume that this is a positive charge in this field, and this is another positive charge in this field. And so what I want you to do is to figure out what would those charges be that would create a positive charge to move in this direction or a separate positive charge to move in this direction. And hopefully you thought through that they both can't be positive because if that were the case, then my positive charges would be moving away. They can't both be negative because in that case, my test charges would be moving into the negative charge. So one of them has to be positive and one of them has to be negative. Does that make sense to you? Let me say that again. If they were both positive, my test charge would be repelled. It would be moving as far away from it as it can be. This charge would be moving in this direction. This charge would be moving in this direction, away from its positive charges. If they were both negative, then my positive charge would want to be drawn toward it, So I know that I have a combination of a positive and a negative. The easiest one to look at is this one. If this were negative, then you could assume that this charge would be moving in this direction and away from a positive here. So this charge would be moving somewhere over here, probably in this direction. But because this is positive and this is negative, it's going to be moving in this direction. Because if I split it, it would look like this. It would move in this direction because of the because of the negative charge, and if I just spread this out, it would be moving in this direction because of the positive, so that gives it a net effect of moving in this direction. And the same thing is going to happen here. If this is a positive charge and this is negative and this one's positive, then it's going to want to move in this direction, but it's also going to want to have to move, let me see if I can draw this out, in this direction. So again, I split the difference and it's going to move in that direction. Because this is negative and this is positive, it's going to create a field around it that is going to influence my test charge. So let's talk a little bit about the test charge. The test charge is influenced when put around the box, and by convention it is positive. By my convention, and typically other classes, but again, that's not universal, but we will always consider it to be a positive charge. And I'm going to get rid of this because I'm going to be doing some other drawings later on. So I'm going to get rid of this. All right, so my test charge is going to be what I put into the field to measure the field, but not to affect the field. Now that seems kind of bizarre that I can put my test field in there and yet I can say it now doesn't create or change the field. Because what we're going to do is we're going to pull our test charge out. So we put it in and then we take it out. So it's what was the field before and after the test charge. How can we do that mathematically? Well, okay, first of all, let's talk about what the field is. The field is, it is a property of the space around the charges that are already there, and it is the area of influence. It is a property of space. That space is changed because there is a charge in it now. And the change is that it now has an electric field that can influence any other charge that comes into its vicinity. And the strength of the electric field will determine how much influence it has. And of course, you can assume that the strength of the field is going to be dependent on the strength of the charges and the distance away from the field that you are. Directly related to the strength of the charges, indirectly related to the distance away from the charges. Okay, think of it as you would think of a magnetic or a gravitational field. And just go online. I am going to do this with the students on Tuesday. But go online and look for a video of iron filings in a magnetic field. And you're going to get that exact same picture with an electric field. And remember that it's kind of imaginary. I mean, the field exists, but how we draw the field is just kind of how we visualize it. There aren't actually lines in the field, but that is the best way to visualize the strength of the field. And forget that I said that it was imaginary. It is not something that you're going to be able to see. Imaginary wasn't a good word. So think of the electric field, that area of influence around a charge. Think of an electric field as you would think of a gravitational field or a magnetic field. All right, now this is how we quantify it. First of all, here is the formula. The field, E is the electric field, is equal to the force of the charge that is there and the charge or the force that it exerts on my test charge divided by the test charge. By dividing it by the test charge, I've put the test charge in and then I've quantitatively taken the test charge back out again. If I just want to find the force, and I know the field, then I can multiply the field times the charge on my test charge. So if it's 1 coulomb, if it's 1 times 10 to the negative 16 coulombs, whatever, I can multiply my field by that. And another way of doing it is I can actually write it all out. And in the past, I didn't used to let students do this, but I am going to let you do it now. This becomes a very complicated equation because you've got your KQ1 Q prime, which is my test charge, divided by R squared, divided by Q prime. So you'll notice that the Q prime goes in and can be taken out right away. So that my actual equation is KQ, which is the charge that was in the field to start with, all over R squared. Now, like I said, in the past, I used to require that students put the Q prime in and actually cancel it out as they're doing the math, because I wanted you to remember that what defines the field is putting a Q prime in there, but that you have to take Q prime out so that you're not actually affecting the field, just defining it. But with remote students and not being able to talk about it as easily, I'm eliminating that step, and you can just jump right to this equation where the Q prime is taken out for you already. All right, E stands for the electric field, and it is measured, as you might guess, because it's F, newtons, over Q prime, coulombs. Its unit is newtons per coulombs. It is a vector, and it does have direction. F is the electrostatic force between my charge that is already there and the test charge that I'm putting in and then taking out when I'm done. Q prime is the positive test charge, which has an unknown magnitude, but it has a unit of C. So I can go ahead and put it in and take it out because it has the appropriate unit to do that. Again, for us, it's going to be a positive test charge. And we will deal with the direction of the field, assuming that our Q prime is test charge. My Q prime is always a test charge, that it's positive. All right, now let's deal with an example of this, and I'm going to cover up the bottom just so that you're not confused with all of the drawings going on here. And I've written kind of small. Hopefully you can see all that. So here's my drawing. I have a test charge right here, and I have a, by the way, because this is a vector, you add fields like you would add any vector. Keep that in mind. You're going to add the fields like you add the vector. So I'm going to find the field because of this, the field because of this, and that will give me my net field, my field overall from where I am putting my test charge. What is the field that it is experiencing by being put here? It's a field created by this charge, and it's also a field created by this charge, and the combination of the fields is a vector combination, and I get that what I'm experiencing right here. All right, so you remember that the formula is K Q1 times Q prime, but then we cancel the Q prime out because it's also Q prime in the bottom, all over R squared. You do the math to find the field between my test charge and this charge. Nope, I'm sorry. Between my test charge and this charge, and I kind of messed up because that shouldn't be 0.4. Okay, I'm going to pause this.